All right, let's discuss the basic concepts of probability. I really can't emphasize this enough for us to really get this, if nothing else, out of probability. And it goes as follows. The notation P of A represents probability, but the probability is always between 0 and 1. Can it be 0? Yes. Can it be 1? Yes. Can it be negative? Can it be larger than 1? The answer is no to both of them. So you want to be very careful. So that's an extremely important property of probability. The other one is that the probability should add up to 1. The only time it doesn't, so this is the first one, this is the second one. The only time it doesn't, if we do it due to round of error. So that's why we want to carry a lot of decimals. Again, for the sake of homework, you got to follow how many decimals they want you to put in to get full credit. But generally speaking, if we put a lot of decimals, it adds up accordingly. And the only time that it is okay if you end up with the sum that is very close to 1. Because of the round of error, you may end up with 1.00000001, something like that, or 0.99999. That's okay because it's due to round of error. Otherwise, if you write it as fractions, add them up precisely, it ends up being total of 1. Now, if an event cannot occur, we call it an impossible set. That means the probability is 0. When an event has a probability of 1 or 100%, we call it a sure set. So probability is 1 or 100%. Now, the next one is complementary event. The notation is A bar. Sometimes they call it A naught. It consists of all outcomes that are not included in the outcomes of event A. In other words, probability of A complement is 1 minus the probability of A. Many times people confuse the odds with probability, and the reason they do, because odds is discussed when, for example, you play lottery and so on and so forth, but they are not the same. The reason they could be close, if the probability is small, extremely small, then the odds and probability become almost the same. But if the probability is not that small, they're completely different. So the way the odds are defined, the odds, normally when we hear that, it's defined as odds against an event A. So against an event A, it is defined as probability of A complement over the probability of A. And it is normally expressed in the form of A to B, where both of them are integers, whole numbers. Now, the actual odd in favor of an event is P of A over P of A bar or A naught or A complement, okay, the reciprocal of that. So if odds against an event is A to B, then for it would be B to A. And this is the probability. This is the odds. This one is close. It is close to probability of A. If probability is extremely small. And that's why the confusion. I want to make sure everybody's comfortable with the concept. So with that being the case, the next thing we want to define is a payoff odds against an event. Payoff odds is defined as net profit over the amount of bet. So therefore, if you do the cross product, A over B equals C over D, then AD equals BC. This is known as a cross product. So net profit times the denominator for the left side is 1. So simply net profit is payoff odds against an event A times the amount of bet. Normally, we want to come up with the exact fraction or decimal. Exact fraction is always better. Again, you just follow the instruction. When we are rounding, we go with 3 significant digits. Basics of probability.
Probability can be defined as the chance of an event occurring. It can be used to quantify what the odds are that a specific event will occur. A probability experiment is a chance process that leads to well-defined results called outcomes.
An outcome is the result of a single trial of a probability experiment. An event consists of any collection of results or outcomes of a procedure. A simple event is an outcome or an event that cannot be further broken down into simpler components.
A sample space is a set of all possible outcomes or simple events of a probability experiment. How to interpret probability values, which are expressed as values between 0 and 1. A small probability, such as 0.001, corresponds to an event that rarely occurs. Odds and their relations to probabilities. Odds are commonly used in situations such as lotteries and gambling.
So one of the things that is extremely important here is the concept of a sample space. It is the collection of all possible events. So that's important for everybody to know. What I'd like you to look at, this is something that is used by statisticians. When you look at the values of probabilities, of course, we said 0 is an impossible set and 1 is a sure or certain set. In between, of course, everybody knows the meaning of 50-50. Likely is close, is up there, close to 100%, if you will, and unlikely is close to an impossible. So that, but it doesn't have a specific value. Just to give you an idea, let's start with a simple example to make some sense out of this. We want to come up with a concept of a sample space. So look at an experiment of tossing a coin. We have only two outcomes, heads and tails. That would be writing as H, T. That would be shorthand notation. So that would be a sample space. The sample space contains two outcomes. We roll a die. A normal die has 6 sides, and it starts from 1 and it goes all the way to 6. There are 6 outcomes. True, false, it just says true and false. There are 2 outcomes, and it works like tossing a coin as far as the number of outcomes. There are 2 outcomes. Now, what happens if we toss a coin 2 times or toss 2 coins? Now, it's important to understand how that works. And there are 4 outcomes, and it can be done by the method of tree diagram as follows. For example, HT. A tree diagram is that the one that puts the outcomes on a branch. So this is the first stage, or you can say the first toss or the first coin. Now, in order for you to go to the next, it is a good idea to keep the track by having the H at top again and T at the bottom. Does it make any difference if you don't do that? No, but it helps if we are consistent. And so this one is H, HT, TH, and TT, giving us 4 outcomes. So this is one way to come up with the answer. Basically, the number of outcomes raised to the power of number of stages. We have 2 outcomes, if you will, and there are 2 stages because there are 2 cones, so it's 2 squared or 4 outcomes as a sample space. If we have, let's say, 4 coins, the number of outcomes would be 2 to 4. If we have 5 coins, we have 2 to the power of 5, 32. So the number of outcomes per stage, each coin has only 2 outcomes, and that is being raised to a proper power. We are continuing with the concept of a simple event and sample space. We are looking at the table given. We're going to use B to denote a baby boy and G to denote a baby girl. So procedure and experiment. Single birth, the event could be 1 girl, for example. So what would be the sample space? We're going to use B and G. But what if we have 3 births? An example of an event would be 2 boys and 1 girl. It's important to see that if we say 2 boys and 1 girl, there are different ways that they're going to happen. So just for the sake of argument, what do we mean by BBG? That means the first is a boy, the second is a boy, and the third one is a girl. But what do we mean by BGB? The first one is a boy, the second one is a girl, and the third one is a boy. And so I think everybody gets the picture. And so For each birth, there are two possibilities. Because there are three births, we have 2 cubed, or 8 outcomes. And you can easily do the tree diagram that was mentioned. As an example, you can say B and G, then this goes as to the second stage or the second birth, and this is the third one. This is one stage, meaning the first, the second, and the third. And as you can see, for example, the top would be B, B, B. That's how you write it. You can write it out, and there ends up being 8 outcomes. Now, what's a simple event? One birth, the result of one girl in a simple event, and so is the result of one boy. If we are looking at single birth, so the very first case. Now, in the next case, when we have 3 births, the result of 2 girls followed by a boy, as an example, GGB as an example, that is considered a simple event. However, the event of 2 girls and 1 boy, I want you to see the difference between these two. When you look at this one, it's very specific, very specific. GGB, 2 girls and 1 boy, in that order. But this event, 2 girls and a boy, in any format that works, and there are 3 outcomes. This is no longer a simple event. It is known as a compound event. So as mentioned before, the sample space consists of 2 cubed, or 8 outcomes, or 8 simple events as listed above. We want to find the sample space for rolling 1 die and then 2 dice. First, I think 1 is very clear. There are 6 sides, and therefore there are 6 outcomes, numbers 1 through 6. But how many outcomes do we have in the second case? There are 2 stages. In each stage, we roll a die, or you can say rolling 2 dice. It works the same way. Each stage contains 6 outcomes. There are 2 of them, so it would be 6 squared. If we have 3 of them, it would be 6 cubed, so on and so forth. That's the way it works. Now, one easy way to put them together is using this table. See how it works. You go from 1 to 6 at top row and the left column, and you put them together. You start with 1, 1, 1, 2, 3, 4, 5, 6. So that would be 1. And then you go all the way down in the same manner. Now you do it with number 2 and number 3, and eventually the last one would be 6, 6. And so there are 6 squared, 36 outcomes. And what I want you to pay attention to is the formula that I'm going to give you. It's not in the text. How do you find n of s? Or sometimes they call it just s, the sample space, the size of a sample space. That would be the number of outcomes per stage. What do we mean by that? You toss a coin, there are 2 outcomes. You roll a die, there are 6 outcomes. That would be number of outcomes in each stage. Now, to the power of number of stages, what do we mean by number of stages? Well, 2 coins, that means 2 stages in essence. Or 4 birds, that means 4 stages. When you roll a die 5 times, that means the number of stages is 5. This is a good question as a probability warm-up. What is the probability of getting snake eyes? When we get 2 ones, it's called snake eyes. What would be the probability of that? Any ideas? Anybody want to share with us their answer?
1 out of 36.
Beautiful. Beautiful. 1 over 36. because the probability is defined as, so probability of an event is n of a over n of s. So the number of ways event A can happen over the whole sample space. Event A, in this case, there's only one way, which means 1, 1. There is no other way. So there's only one outcome. The numerator is 1. And how many outcomes total? 36. And we're done. All right, let's move on. Common approaches to finding a probability, there are 3 of it. One is the classical approach. Classical probability uses sample spaces to determine the numerical probability that an event will happen and assumes that all outcomes in the sample space are equally likely to occur. And we have seen those examples already. And in short, the probability is defined as the number of the outcomes that we are interested in over the total number of possible outcomes. The total number of possible outcomes is known as sample space. Now, I'm showing you different notations here. In some cases and in some text, S is used to represent the sample space. Now, I want you to be exposed to that, but I want you to realize at the same time, we are not bogged down with just the formula that they give us. We understand the concept. And so as an example, probability of even number in roll of a dice would be the total number of even numbers that we have. We have 2, 4, 6. There are 3 of it. Over the total number of outcomes, there are 6 sides. So 3 over 6. Needless to say, we can simplify it as a 1/2. In the case of an empirical probability, known as relative frequency also, or approximation of probability, we have an observation, if you will. So we conduct or observe a procedure and count the number of times that event A occur. P of A is then approximated as I mentioned in the previous one, n of A over n, if you will, or n of procedures repeated. It's important to know the total number of outcomes is always, the denominator is always the sample space. And the specific event of interest, that would be the total number of that happening as the numerator. So probability of randomly selected student from a statistic class to be a female, for example, would be the number of female students over the total. Okay, so just for the sake of argument, if we have 40 students in class, let's just say 21 students are females, would make it 21 over 40. That's just an event that follows relative frequency as an approximation. So with that being the case, let's look at this last one.
Subjective probability. P of A, the probability of event A, is estimated by using knowledge of the relevant circumstances. A subjective probability can be estimated in the absence of historical data. Uses a probability value based on an educated guess or estimate, employing opinions and inexact information. Experiments that have neither equally likely outcomes nor the potential of being repeated are assigned by subjective probability. Examples: weather forecasting, predicting outcomes of sporting events.
This last paragraph.
Simulations. Sometimes none of the preceding 3 approaches can be used. A simulation of a procedure is a process that behaves in the same ways as the procedure itself so that similar results are produced. Probabilities can sometimes be found by using a simulation.
Sometimes it's either impossible to do a procedure or it's easier to do the simulation. It can be done that way, and computer or technology is used to do so. We want to look at this example. When a single die is rolled, what is the probability of getting a number less than 7? And simply put, if you call the event E, probability of E is n of E over n of S. If you call it A, probability of A is n of A over n of S. And the denominator is the sum. We already know there are 6 sides, so we already have the idea as far as the denominator. As you know, all numbers obviously are less than 7. So this is a sure event. Because every number is less than 7, 6 over 6 gives us 100%. And this is known as a sure set or a certain set. The next one is asking for numbers that are larger than 2. So what numbers are larger than 2? You can just write them out. If you write those numbers, you see there are 4 of them. So pretty much 4 over 6 or 2/3. Even numbers, again, you can write them, and that gives you 50%, 1/2. Finally, the number that is larger than 7. Is there any number that is larger than 7? And we don't have that. So that can't happen. That is known as an impossible set. Here's the next example.
For the gender of the children, if a family has 3 children, use B for boy and G for girl. Use a tree diagram, a graph of possible outcomes of a procedure to find the sample space for the gender of 3 children in a family.
As I mentioned before, the number of outcomes, the total sample size, is the number of outcomes per stage to the power of number of stages. In this case, there are 2 outcomes and there are however many children, 4 children, 5 children, 8 children. That would be the exponent. In this case, 2 cubed equals 8. If we look at the tree diagram, again, we want to be consistent. So branches B and G. If you put the B at top, you just keep on with the same thing. If you put the G at top, the same thing. Just be consistent. The next one happens. Take a look at the next stage. That means the next birth in this case. So for the sake of argument, if we had 2 births, it would be BB, BG, GB, and GG. But there is one more. This is the 3rd stage. And so the very top one gives us B, 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 and the very bottom one gives us G, 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 and anything in between. And so we write it out in a set. We use braces to represent a set. So we got the sample space. So if a family has 3 children, find the probability that 2 of the children are girls. So let's see how we arrive at it. It simply means we are looking for 2 G's, and that's why I put them in a different color. When we go back to this either tree diagram or the set, we notice this one, and this one contains 2 G's. And of course, we really need to understand the meaning of it. So I'm going to repeat because I said that last time, but it's extremely important to understand the meaning of BGG versus GBG. When you look at the first one, this means the first birth was a boy, the second one was a girl, the third one was a girl. Whereas GBG means the first one is a girl, the second one is a boy, and the third one is a girl. And so there are 3 of them out of 8. So that's how we arrive at 3 over 8. Here's a relative frequency example, an empirical probability.
If there were nearly 3 million skydiving jumps and 24 of them resulted in deaths, find the probability of dying when making a skydiving jump.
So according to this, we just use the relative frequency, 24 out of 3 million. That's the idea. So we use the empirical approach. The classical approach cannot be used because 2 outcomes, dying and surviving, are not equally likely. However, conceptually, they are similar in that basically we use the n, in essence, n of a over n of s. Okay, conceptually, they're very close though. So with that being the case, P of death is n of death over n of skydiving, which is 24 over 3 million. We simplify and we get 0 point bunch of zeros and 8. Now, it's important to know Although at some point it was mentioned maybe 3 significant digits, we don't want to mix them up and make a mistake with the number of decimals that one can use. In this case, if somebody says, okay, I'm going to use 4 decimals, for example, or even 3 decimals and things like that, you may end up with 0. So it's really not a good practice. If need be, you carry out more decimals. It's important to pay attention to that.
In a high school, it was found that 450 of them texted while driving in a semester and 550 did not do so. According to these results, if a high school driver is randomly selected, find the probability that he or she texted while driving during the same time period.
We can set up this table. Those who texted, the size is 450. Those who didn't is 550. We are dealing with a total of 1,000 students. We use the same relative frequency, if you will. 450 over 1,000 is the answer. Now notice, of course, you can write it as 0.45. If you want to keep it as a fraction, it's absolutely fine. You get 45 over 100. And then you can divide the top by 5 and the bottom by 5. So if you want to report this as a fraction, perfect. Make sure you have 450 over 1,000 so your reader can see where you get the numbers from, and then the simplified version. So you really want to show your reader both of it. This one is to tell him, okay, where I get the numbers from. And the last one shows, okay, I know my math, I can simplify. There is a 45% or 0.45 probability that if a high school driver is randomly selected, he or she texted while driving during the last semester.
In a sample of 50 people, 21 had type O blood, 22 had type A blood, 5 had type B blood, and 2 had type AB blood. Set up a frequency distribution and find the following probabilities. A person has type O, a person has type A or type B, a person has neither type A nor type O, a person does not have type AB.
So we have the type in one column, A, 22, B, we are going in an order of alphabetical order in essence. You don't have to do that by any means. You can start with O and write 21. But at A, we have 22 of them. B, there are 5. A, B is 2. And O is 21, total of 50. So that would be the frequency distribution table. So let's look at the first one. It says a person has type O blood. So type O is what? How many? You want N of O over N of S in essence. So 21 over 50. So you have 21 of those. And so you're going to write 21 over 50. If it gets simplified, so be it. If not, you can leave it. So that would be part A. Part B is asking a person has type A or type B, and there's nothing in common. So A and B, we add them up. 22 plus 5 over 50. And again, we simplify if we can. The next one, a person has neither type A, that means type A is out, nor type O. So A is out. I'll put the X mark next to it. That means forget it. O is out. I'll put the X mark next to that. So what is left is B and AB, 5 and 2, 7. So 7 over 50. 7 over 50. The last part D says a person doesn't have type AB. So that means AB is out and everything else is in. So I put a red circle next to it. So that means AB is out. So basically 50, 2 of them is out, is 48 over 50. And it ends up being 48 over 50 or 24 over 25 because we need to simplify whenever we can. The concept of a complementary events. As far as the probability is concerned, probability of A complement or A bar or A naught is known as 1 minus probability of A, complementary events. Let's read these events. Rolling a die and getting a 4. A complement of that would be everything except 4.
Selecting a letter of the alphabet and getting a vowel. Getting a consonant, assume Y is a consonant.
Next,
Select getting a month that begins with a J.
the answer is
Getting February, March, April, May, August, September, October, November, or December.
everything except the ones that start with J, obviously.
Selecting a day of the week and getting a weekday. Getting Saturday or Sunday.
So the complement of an event A denoted by A bar A naught consists of all outcomes that are not included in the outcomes of event A. Therefore, probability of A naught or the complement of A can be calculated as 1 minus probability of A.
If there were nearly 3 million skydiving jumps and 24 of them resulted in death, find the probability of not dying when making a skydiving jump.
We've already done the calculation, 24 out of 3 million. The complementary event is of interest to us. 1 minus that. It's important to see according to the given, we want the probability of its complement. 1 minus 0.000008. We need to carry out a lot of decimals.
More boys are born than girls. In one typical group, there are 205 newborn babies, 105 of whom are boys. If one baby is randomly selected from the group, what is the probability that the baby is not a boy?
So what we are looking at, the idea of a complementary event, probability of not a boy, B complement, B not, 1 minus the probability of boys, that becomes a probability of girls. 100 over 205, or you can say 205 minus 105 over 205. However you want to put that, you can simplify the fraction. If you simplify the fraction, divide by 5, 20 over 41, or you can put it into a decimal format. The actual odd against event A.
The actual odds against event A occurring are the ratio P of the probability of the complement of the probability of the event, usually expressed in the form A to B or A to B, where A and B are integers having no common factors. The actual odds in favor event A occurring are the reciprocal of the actual odds against the event. If the odds are against A are A to B, then the odds in favor of A are B to A.
It's important to pay attention to the definition of odds. Most of the time, we are interested in odds against, but understand, odds for, in this case, odds in favor, is written as O of A is P of A over P of A naught, P of A bar, P of A complement. The actual odds against, look at this one. This is the two are reciprocals of each other. So that's the definition. And I want you to look at the actual odds in favor. When you look at that, odds for A has the probability of A at top. If the probability of A is extremely small, then probability of its complement is almost 1. And that's why they seem to be the same. So when the probability is extremely small, for all practical purposes, they become the same. But they are not. And that's important for everybody to know. And so you have the definition of a payoff odd.
The payoff odds against event A represent the ratio of the net profit if you win to the amount bet. Payoff odds against event A equals net profit to amount bet. Payoff odds against event A, oh, I just did that. Net profit equals payoff odds against event A times amount bet.
So payoff odds against A is the ratio of the net profit to the amount of bet. So therefore, what is your net profit is the product of the two, the payoff odds and the amount of bet that you put in. Let's look at an example.
If you bet $5 on the number 13 in roulette, your probability of winning is 1 in 38, but your payoff odds are given by casino as 35 to 1. Find the actual odds against the outcome of 13. How much net profit would you make if you win by betting $5 on 13? If the casino was not operating for profit and the payoff odds were changed to match the actual odds against 13, how much would you win if the outcome were 13?
let's stick with the definitions. So we want to find the actual odds against the outcome of 13. So we follow the formula. At the very top in blue, we have the formula and we just put it in. Remember, the probability of winning is 1 over 38, and that is the probability of A. So the top is 1 minus 1 over 38. The bottom is 1 over 38. This is a simple case. We get 37, and we normally write it as 37 over 1 or 37 to 1. I want you to pay attention why I wrote it as 37 over 1, because they like us to write it as a ratio of two integers. So 37 to 1. And I'm assuming everybody's comfortable with the complex fraction and can simplify it for the problem. When you're looking at this fraction, which is a complex fraction, you can multiply the top and the bottom by 38. It goes away, becomes 37. And we write 37 as 37 to 1. So that would be the actual odd against the outcome. So how much net profit? We mentioned the net profit is basically the product of the payoff odds and the amount of bet. Now, what is the payoff odds? So using that, 35 times 5, I'm using the formulas that we have discussed. Net profit, we said it's payoff odds against an event times the amount of bet. And the payoff odds by casino, they give us 35 to 1. So it's 35 times the amount of bet was $5. So it's $175. Now, it is extremely important for us to understand how much we collect. We collect $175, and the amount of bet is not going away. So we keep our own $5. This is the way the payoff odds work. So I want you to be very careful when you look at this versus when you play a lottery. If you pay $2, $3, $1, $5, however amount of money that you pay for lottery, when you win, the amount that you paid will come off as your net gain, if you will. Whereas here, the amount of money that you put in to play, it's not gonna go away. If you break even, they don't touch your bet. If you lose, they take away your bet. If you win, your bet is intact, and then they give you $175. That means you keep your own money, okay? So it is your net profit, which is 175. This is something that I've seen students sometimes making a mistake with, so be very careful with that. Having said that, so if the casino were not operating for profit, obviously they are, then the payoff odds wouldn't be 35 to 1. The payoff odd would be what we found in part A. So they got to give us 37 times that. So pay attention where number 37 to 1 comes from. That comes from part A. We did the calculation. So they would give us 185. And obviously, if they paid, that would be considered a fair game. And they wouldn't make any money. And that's why they don't pay as much.
Professor, I just have one question.
Go ahead.
When it's the 35 over 1, I get that what happens to the 1? Because I understand that 35
It's 35 to 1. That means 35. In fact, if you look at part A, the answer is 37. But the way we want to represent that, instead of saying 37, okay, so for example, part A is 37. So for part A, we say 37 or 37 to 1 or 37 to 1. They want us to show it in one of these two formats instead of saying 37. So that one is, that means we get 37 times as much. Does that answer your question?
Yeah, thank you.
The way it's set up, when we discuss the odds are discussed with integers. So you are dealing with a fractional format. The numerator is an integer, the denominator is an integer. Anytime the denominator is 1 in math, we get rid of it. Remember that. But in the concept of a payoff odds and odds, we keep it. That's really the bottom line for that number 1. But it may be like it's 7 to 2. Now, what does it mean if we say 7 to 2? It means really 3.5 times. That's the idea. If we said, for example, 9 to 2, that means we get 4.5 times. In this case, we get 37 times, or if it's 35 to 1, we get 35 times. Law of large numbers and identifying significant results with probabilities. Law of large numbers.
As a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability, and it applies to behavior over a large number of trials, and it does not apply to any one individual outcome.
The rare event rule for inferential statistics. If under a given assumption, the probability of a particular observed event is very small and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, we conclude that the assumption is probably not correct. Using probabilities to determine when results are significantly high or significantly low. Significantly high number of successes. X successes among n trials is a significantly high number of successes if the probability of X or more successes is unlikely with a probability of 0.05 or less. That is, X is significantly high number of successes if the probability of X or more is less than or equal to 0.05. Significantly low number of successes. X successes among n trials is a significantly low number of successes if the probability of X or fewer successes is unlikely with a probability of 0.05 or less. That is, X is a significantly low number of successes if the probability of X or fewer is less than or equal to 0.05. The value 0.05 is not absolutely rigid.
The idea of law of large numbers and identifying the significant results is that there are cases we don't expect it to happen. The probability of something happening is extremely small. But if it happens, it means something is working or something is not working. For example, if there's an intervention, couple, for example, is trying to have a next birth to be a boy or a girl specifically, and if they are working with some institution, if it happens that when they look at a number of cases, the probability that, for example, if there are 100 births and the claim of that institution is that we can make it happen, for 100 births there ends up being, let's say, 52 girls instead of 50 on the average. It's really not that significant, but if it happened to be 70 or 80 or 90, and that is a rare event, then you claim that it is effective. So here's another concept of law of large numbers. A coin is tossed 100 times and we get 98 heads in a row. Assumption, the coin is fair. A normal assumption when an ordinary coin is tossed. Everybody understands the meaning of a fair coin. A fair coin is that we expect 50-50. And so if the assumption is true, we have observed a highly unlikely event. It can't happen. Okay, that's sort of boy, is that impossible or what? So according to the rare event rule, therefore, what we just observed is evidence against the assumption on this basis. We conclude the assumption is wrong. The coin can't be fair. It must be loaded.